Hello. Hello. Sir, am I audible?
Hello. Yes,
Yes,
sir.
sir.
Good afternoon.
Good afternoon. Good afternoon. Am
Yeah,
I
you
audible?
are audible, sir.
Yes, sir. Namaste.
Namaskar, sir. Ah, we can wait 2 or 3 minutes.
Yes, sir.
Good afternoon, sir. Good afternoon. So, do you have the Excel sheet which I have given?
Yes, sir. I have the Excel sheet. है
Okay,
मेरे
okay.
पास सर वो.
ठीक है.
हाँ. It will start from M Sripad. Paper ID G10005.
Dr. Sumit Bhardwaj also joined.
Yes, sir.
So today's session chair is Dr. Santosh Mani and session co-chair is Dr. Sumit Bhardwaj. So welcome Dr. Sumit Bhardwaj.
Thank you, sir. Thank you.
Yeah.
I think my video is okay. I will change the. Am I audible, sir?
हाँ सर, ऑडिबल हैं आप.
Thank you, sir. Thank you. I will. Background effect.
So just to check, M. Sripad is there in the meeting. Chinta is there in this meeting. Dr. Chandrasekhar is there in this meeting.
Yes, sir, I'm here.
Okay, okay, sir.
So can we start, sir, now?
Yes, I think we should start, sir. Now it is
Yeah.
2-1.
Whoever present in the meeting, we can start from there, and
Yes.
participant will join later also. So I'm formally welcoming both the session chair in this parallel session third B, and instructions to participants. Actually, we are giving 8 minutes to presentation and 2 minutes for query only. So please bind up your presentation within the time limits. So now I'm handing over mic to the session chair.
Thank you, sir. So, dear participants, let's start. As sir has already informed that you have to wind up your entire research discussion within 8 minutes, and the 2 minutes are given for the question answer. So, the paper ID G1 0005 M Sripad. Okay. Paper ID G1 0006 Miss Chinta. Okay. Paper ID G1 0007 Dr. Chandrasekhar. Sir, are you there in the meeting?
Yes, sir. Welcome, sir. Chair Santosh Mani, sir. And Sumit
Yes.
Bhardwaj, sir.
Yes, sir, you can start.
Yeah, sir. I'm going to share my screen, sir. Sir, please enable, sir. Sir, I'm requesting, please enable sharing here.
Manoj sir, we have to make him a co-host.
Yes, sir.
To give a right question.
Manoj, sir.
Yeah. Just a minute, sir. Just a minute. I'm doing. Yeah, now you can share the screen.
Right, sir. Thank you, sir. My screen is visible, sir.
Yes, sir, your screen is very much visible.
Yeah.
You can start.
Thank you very much, sir.
Go to
see,
the
and share.
slideshow.
Yeah, okay, sir. 1 minute.
So I'm putting a timer. After 7 minutes, the ring will come, and then in 1 minute you have to wind up.
In the bottom right side.
Yes, sir.
Yes.
Is it okay, sir, now?
Yes, sir. Everything is fine. You can start.
Yeah. Okay, fine, sir.
Just
Thank you,
just
sir.
switch on your video, sir, if possible.
What, sir? Video. Aha, okay, sir. Right. 1 minute. I'm going back. So, right,
Yes,
sir.
sir. We can see. Please start.
Okay, sir. So, see, sir, my title is actually Transition Metal Doped Radiation Shielding Glasses, sir.
Okay, sir.
Yes, and my see, see, my research is on to prepare the glasses using this composition 30 minus X PPFT and X Al2O3 10 Ba2O3 59 B2O3 as doped with transition metal manganese oxide, sir. So here I prepared two series. One with lead fluoride and another one is calcium fluoride bearing aluminum oxide. See, my intention is to compare the radiation shielding properties. See, one is with the lead and another with is non-lead because lead is toxic. That's what I'm. See, my intention is intention is to replace that lead with the calcium fluoride. That is the main intention, and I'm compared with taking radiation shielding parameters. Right. So here, see, actually, so this is the principle.
Sir, sorry to interrupt you. Can you just click on the slide mode that is on the
Right, sir.
bottom?
Yes. Okay, sir. Yeah. So this is the principle, sir. Here, this is the radiation source. This is, and here this is the material, glass material. There are so many different types of materials are there, like concrete, glass materials, water, and lead containing glasses, other glasses also there. But so many cases we cannot use concrete and water. So based on their area and environment. So that's why certain circumstances we use glasses. So and the radiation shielding parameters properties also depends on or varies based on the material and the composition of the glasses. So because I have chosen glass because glasses are so very interesting efficient materials so which are being used as smart glasses and in other areas also in medical field and so in radiation field also just that's what I have chosen the glasses particularly bored glasses, right? I'm going to so characterize see the prepared glasses so using PHYX PSD software codes are here and the parameters. So here I calculated, I measured our linear attenuation coefficient and mass attenuation coefficient and off value layer and effective number of atoms. So these actually properties which characterize the ability of a material to attain or absorb the radiations. So that's what here LAC and MEs are very important. And so here HVL is the thickness of the material. Okay, so which lowers the radiation so intensity to off value. So that is the HVL, and here the effective number of atoms also plays very important role because here it gives the number of electrons participating so in photon atom interaction. So thereby so it attenuate If number of atoms is more, attenuation will be more, as I found in my two series of glasses. So that's why I prepared these glasses. I characterized this linear attenuation coefficient and mass attenuation coefficient of value layer and effective number of atoms. So here I'm going to show you, sir. Here these are the graphs represent mass attenuation coefficients. Sir, I prepared here PB. This is the code PBM1 to PBMN5. So it is clear that, sir, from these graphs here, as the photon energy increases, see here the mass attenuation coefficient is decreasing. Right. See here from the sample 1 to 5, it is decreasing. Why it is decreasing means the lead is replaced with aluminum oxide, where lead actually having high Z, that is atomic number, whereas even so mass of the lead fluoride is much greater than the aluminum oxide. So here the value is decreased from M1 to M5, that is as aluminum oxide is increasing, lead is decreasing, 86.74 centimeter square to gram per gram to 74, sir. In the case of calcium also, it is decreasing from 59 to 15, 56 to 12. So it is due to, actually the main reason is, apart from the mass of the lead fluoride, here actually the photoelectric effect plays a vital role. So that's why here as the photoelectric effect is decreasing, here also the value of MAC also decreasing. See here. So this is, but here the value of the calcium oxide, maximum value of the MAC is less than the lead fluorides. But why I'm taking here, I'm comparing with the calcium fluoride, sir, because it is non-toxic. Calcium fluoride is stable and it is non-toxic. So that's why I replaced that with the lead fluoride, sir. And here, so this is linear attenuation coefficients are also, sir. So here also it is decreasing because here the linear attenuation coefficient is inversely proportional to the energy. So as the photon energy is increasing, here also it is the value of LAC also decreasing, but it is between 0 to 0.1 to 0.02, it is less. So the decrement is very less, but whereas when it is reached to 0.05 mega electron volts is gradually decreases, means slowly it is heavily it is decreased. So here the cause is same thing as Z, so number of atoms, that is atomic number is lead for lead and bismuth is 4. So and so initially, when compared to the calcium, so it is lead, the glasses having lead and bismuth showing high linear coefficient values here. So the values are given here. For LAC of bismuth is 930, 338, 398.48, and it is decreased to 314. But whereas calcium, it is 290. 398 is maximum value, and here calcium is 290. But lead is absorbing more, attenuating more radiation when compared to the calcium, sir. So this is half value layer. Here also a gradual increase is there. So, but at low value, at a low value.
Sorry to interrupt you. Just try to wind up in a minute.
Yeah, sir. Okay.
Yes.
This is next one, sir. And here also values of value layer also. Actually lead is high because when compared to the means calcium fluoride glasses, it is increasing with the photon energy value. So this is the about half value layer, and this is effective number of atom, as I mentioned, as Z is more for the lead. So here the effective number of atom is more for the lead containing glasses. But when I am comparing with the calcium fluoride glasses, because they are very stable and non-toxic, so that's why I prefer for the radiation purpose the calcium fluoride glasses are good enough for attenuating the glass with radiation, sir. So these are the conclusions. HV MAC values or LAC values, HVLS are Z effective number of atoms are also more for the lead glasses, and comparatively calcium glasses are lower values when compared with the lead containing glasses. But as so calcium fluoride glasses are more stable and non-toxic, and so lower weight and cost effectiveness also. So these calcium fluoride glasses are important. So this is about the comparison between the two series of glasses. One is the lead fluoride glasses with manganese oxide. Another one is the calcium fluoride glasses with MnO2 doped, sir. Santosh Mani, sir, I just
Yes, sir. So, very nice presentation. Anybody has any question? Okay. Sir, I have one question, just a quick question.
Sir.
How that LAC value is going to affect the performance of the material that you have created?
Yes, sir. Suppose LAC, just I go for here, sir. I go back, sir, please. Sir, LAC values are actually here linear attenuation coefficient. See, this is actually composition. See, exactly, sir, because here the linear attenuation coefficient is more for lead, sir, when compared to the calcium fluoride classes. But what I'm telling, sir, here, lead is toxic. But as calcium fluoride, even though having so low value when compared to the lead fluoride, so it is non-toxic, cost effective, and is more stable. So that's what I'm preferring, sir.
Okay, sir. Okay, sir. Very good, sir. Thank you, sir. Very good presentation.
Thank you, sir.
If there are no other questions from
Thank you very much, sir.
Anybody else, we can thank the speaker. Dr. Sumit, sir, you have any question?
Done, sir. Move forward.
Okay,
Yes.
thank you.
Next is paper ID G1009. Gujeti Sandhya Rani.
Yes, sir. Yes, sir.
Yes, ma'am, please start. After 7 minutes, I'll inform you. Then 1 minute you have to wind up.
Okay, thank you, sir.
Chandrasekhar sir, please
Sir, you can stop.
stop sharing.
Dr. Chandrasekhar, sir, please stop the screen sharing.
Sir, is it visible, sir?
Ma'am, we are not able to see the slides. Please share.
Is it, sir?
Your slide is not audible, sir, not visible.
Now, ma'am, click on the slideshow and switch on your video.
Okay.
Is it,
Your
sir?
slide
Is
is
it okay, now,
clear.
sir?
Yes, it is okay.
Thank you, sir. Thank you. Sir, this is Sandhyarani Gujeti. I am from Department of Physics, Osmania University. I am working under the supervision of the Aparna Dud madam. Here I am talking about the UV and visible FPR spectroscopic studies of the sodium tetraborate, and it is doped with the calcium nitrate. This is my
Sandhya
point
Rani,
of
sorry to
sir.
interrupt you. Go to the slideshow first.
Sir, is it not visible?
No, no. Still, it is not in slideshow.
Ma'am, just on the bottom side, there is a symbol for the slideshow. Just click on that. Or you can just go to the top, extreme top.
Yes, sir.
There's a slideshow. Please click on that.
From beginning. Yes.
Ma'am, on the extreme left side, you will find there is a from beginning. On that you can click.
I think she clicked over there from beginning, but it is not
Okay.
properly showing there.
Ma'am, you can
Okay.
click from the current slide. Just click on the current slide. Or you can click at the bottom.
Wait, sir.
Still same problem.
Okay, na, sir?
No.
You just actually start and move the slides from slider. Yeah, start you.
Go to next slide.
Go to next slide. Yeah.
Okay, you can continue, no problem. Let's continue.
Yes, you can continue with this, Sandhya Rani. No
Sir,
issue.
in introduction. Sir, is it visible?
Yes, ma'am, it is visible. You can continue.
Thank you, sir. Glass is an inorganic product of the fusion which has been cooled to a rigid condition without crystallization. And the term glass is often used to describe any amorphous solid that exhibits a glass torsional temperature Tc. Of course, the glass is an uniform amorphous solid, and here the atoms are randomly arranged throughout the sample. And this is not having the long range periodicity, this is having only the short range periodicity, and this is as well as having the ionic and the covalent bonding interaction. Actually, a borate has the excellent ability to form the glasses, but it is has the low chemical durability and
Please move
potential
the slides.
toxicity. So to overcome these limitations, the borate is incorporated with the suitable modifiers. Here, the sodium tetraborate is the chemical one of the suitable modifier that is enhance the chemical durability. When it is heated, it is decomposed into the sodium metaborate and the boric antihydrate. Here, the boric antihydrate forms the borosilicate glasses. So the G Sangita is used the sodium tetraborate glasses doped with the copper ions, and that is containing the calcium oxide and the zinc oxide. So which were prepared by the melt quenching method. And MS Burai also prepared the sodium tetraborate glasses by using of the melt quenching method. So that's why I conclude that the sodium tetraborate is one of the useful in the shielding materials and
Santosh
solid
sir,
state batteries.
sorry.
Ma'am,
In
ma'am,
between,
your
slide is
slides are
not
not
moving.
going ahead.
Yeah, yeah. Same issue.
Just click on the slide show. Yes, yes. You are going on the go bottom. Go to the right side. You can see the three icon. And ma'am, switch on your video also. Put the pointer down, ma'am.
Where it is showing percentage, na 78%. You can click here, adjacent to percentage. The
Actually,
third.
this shows sharing.
Ma'am, you stop. You stop it.
Okay, sir.
And then you again start.
Share screen, sir. It is, sir.
Not yet. I cannot see. Yes, ma'am. Now the slides are seen. Yes. Now you just put a double click on that from beginning. Double click. Ma'am, on the top left corner, you just click on that menu from beginning. Put a double
Wait.
click.
Okay, sir. From beginning. Yes,
Yes,
sir.
Yes,
yes.
yes. Put a double click.
Yes, sir.
Even though it is not coming, sir, I
Showing.
think.
Then you can come bottom. You can see the end may on the right side. There is a
Okay,
plus
sir.
and minus ka symbol. Then there is a percentage 73%. The left to that there is one icon. Just click on that. Yes, yes.
Okay, na, sir.
No, ma'am. Put a
No,
double
no.
click. Put a double click on that presentation. Yes, yes. No, no. Go to the right side, right icon, right side. Yes. Put a double click on that. Left double click. Put a pointer on the left double click. Oh, okay, ma'am, you continue. Just click on the next slides.
Sir, this is the PowerPoint द्वारा
No issue, ma'am. You can continue. Just click on the slide while presenting.
Okay, sir.
No
Sir,
problem.
this slide is visible or not, sir?
Slides are visible, but they are not in the slide mode.
Okay, okay.
No issue. You continue.
Thank you, sir. So, calcium oxide is a crucible ingredient in the glass manufacturing. Actually, it is acting as a stabilizer and property modifier.
Ma'am, sorry. Just click on that slide. That you have to move the slide manually. I can see the plan of the talk. I cannot see the introduction.
Okay,
Yes,
sir.
now it is okay.
Yes.
Introduction. Yes.
Glass is an inorganic product of fusion which has been cooled at rigid conditions and without crystallization. Actually, the term glass is often used to describe any amorphous material that exhibits a glass transition temperature Tc. Of course, it is an uniform amorphous solid. Here, the atoms are randomly arranged, and this is having the same refractive index in all direction. This is not having a long range periodicity. This is having only the short range periodicity. Of course, this is also having the ionic and as well as the covalent binding interactions. So actually the boron has the excellent ability to form the glasses, but it is having the a low chemical durability and potential toxicity. So to overcome these limitations, the boron is mixed with the another suitable modifiers, that is here I'm taking sodium tetraborate. This is enhance the chemical durability, and when it is heated it is decomposes into the sodium metaborate and boric antihydrate. So the boric antihydrate forms the borosilicate glasses. G. Sangita have used these sodium tetraborate glasses doped with the copper ions that is contain the calcium oxide and the zinc oxide, which were prepared by the melt quenching method. And A. Burahi also prepared the sodium tetraborate glasses by using of this melt quenching method, but he is using the lead oxide and the chromium oxide in their work. So that's why from this literature I concluded that the sodium tetraborate glass is useful in the shielding material and the solid state batteries. So actually the calcium oxide is a crucible ingredient in the manufacture of the glasses. So it is having the stabilizer and the property modifier, and of course it is enhance the chemical durability and improve the strength also, and the hardness of the glass product, and increase the density of the glasses. So this is the importance of the calcium oxide in the both traditional and the advanced glass formations. And of course the lead fluoride is the another important component, and this is used in the glass system to get the transparent glass ceramics and with specific optical properties and improve the luminescence efficiency. The copper oxide can be used to create the glasses with specific optical properties like a bandpass films, which are used to various applications like medical medicine and the technologies. And of course, particularly in the Cu2 plus state can create the glass that act as a filter for specific UV and visible wavelengths. These are the characterization. Initially, the X-ray diffraction spectrograms were recorded on the CNPC glasses. To know the amorphous nature with the help of the a Philips X-ray diffractometer at room temperature, and the Archimedes principle was used to determine the value of the density of the CNPCS glasses which are prepared by me. And first we have to take the three pieces of the CNPC glasses for the each sample, and after that measure the value of the density and the average value of the density taken for the final value of density for each sample. And the UV visible spectra were recorded on the sample at room temperature using the UV 1800 spectrometer, scanned in the range of the 190 to 1100 nanometers in the absorption mode. And the FTR spectrum of the CNPC glasses was scanned on the JASCO FTR 4200 spectrometer at room temperature in the range of 400 to 4000 centimeter inverse. And this is the experimental methods. Here the sample preparation. So these are the glass composition which was prepared by me. And the sodium tetraborate and the calcium oxides are the variable here, and lead fluoride and the copper oxide are the constant terms here. So all the above chemicals were, I mean, glass samples are prepared by the conventional melt quenching method. And first of all, I took these basic chemicals that are sodium tetraborate, calcium oxide, and lead fluoride, copper oxides, or the are from the unlike grade flucum materials. And first we have to I have to take this mole concentration of these chemicals were weighted in the monopant digital balance, and finally grounded in a mortar. And these chemicals were taken in a porcelain crucible and were placed in the electrically heated furnace, and that is maintained at 1000 degrees Celsius. So these mixture took nearly 45 minutes to melt. And further, these molten mixtures were stirred to achieve the homogeneity. These were poured in the, I mean, a stainless plate, and that is pressed with a stainless steel plate that is maintained at 200 degrees Celsius. So this is annealed at same temperature, and for 200 sorry, that is taken for the 24 hours to relieve the stress. These are the result and discussion. Here the prepared glass compositions are like this. So this is the glass code, and this is the glass samples. So here x is equal to 0, 5, 10, 15, and 20, and these are the glass samples, and these are the images of the prepared glass systems. Yes, so this is a graphical representation of the density and the molar volume of the glass samples. Here the density is increases and the molar volume will be decreases with respect to the increasing of the mole percentage of the calcium oxide. And the decreasing in the density values is represents the increasing of the non-bridging oxygens, and of course that is increase the interatomic spacing also. Yes, this is the X-ray spectra of the CNPC glasses. So I use the Philips X-ray diffractometer. That means at room temperature. So this is some of the few samples shown that the shown in the figure. So here the absence of the sharp peaks is gives the amorphous nature of the glasses. So here the we observe that the absence of the sharp peaks that is revealed the
So, ma'am,
non-crystalline.
last 1 minute. I have already put an alarm. So, last 1 minute, please try to wind up.
Okay, sir. So this is the optical absorption spectra of the CNPC glasses, and this is the absorption coefficient. So we can determine the value of the band gap and the aerobic energy from this formula, and this is the optical band gap formula. So this is a whenever draw a graph between the alpha h mu power of 1 by 2 and the h mu, the tangent drawn at the line segment of this curve, and whenever the tangents are intersecting at the h mu axis, the intersecting point is gives the band gap values. Here the optical band gap values of the CNPC is decreases, that is 3 to 2.181 electric volt, and of course increasing with the CAO of the mole percentage. And the decreasing reveals the structural changes which are happening in the glasses. And this is the Urbac energy plots. This is also I mean the graph is drawn between the log alpha and of course h mu, and the values of these energy levels are 0.5025 to the 0.8818, and this range indicates the less defects in the glass structure. And these are the formula of the refractive index, molar polarizability, and the molar electronic polarizability. And the values of these are all are tabulated below. So like this, here the Orbic energy values will be increased. All are optical band gap, refractive index, and molar refraction, molar polarizability, all values will be decreases. Because of these decreasing of the values will be indicating the, increasing the non-bridging oxygen. So due to that, the oxygen will be deactivated, and of course the glass will be formed. And this is the
What is the
evidence
final
for the
conclusion?
CNPC glasses.
Final conclusion, yes.
Mm, here the 461 is the metal cations, and 552 is gives the boron axis bending vibrations, and 7102 830 is the stretching of the in BO3 units, and 996 is the oxygen boron oxygen vibration takes place, that is at boron axis stretching. And 1125 boron axis and boron extension in the BO4 tetrahedra, and of course the 1250 tetragonal BO3 unit stretching vibrations. 1361 to the 1477, while antisymmetrical lengthening vibrations of boron axis and boron groups. And this is the conclusion. So soda tetraborate glasses doped with the calcium ions and containing the copper oxide and the lead fluoride were prepared by the melt quenching method. And the XRD patterns is gives the amorphous nature of the prepared glasses. And the CNPC values will be, band gap values of the CNPC glasses will be decreased, that is from 3 to 2.181. And the decreasing of these value will be what reveals the structural changes which are happening in the glasses. And Orbic energy values will be increasing, that is tells less defects in its glass structure. And of course the refractive index RM alpha m values will be decreasing with respect to the increasing of the calcium oxide of mole percentage. So these are the references. And I would like to thank to the organizing committee of the ICC 2025 and my department of physics and my supervisor Dr. Aparna madam and Chandrasekhar sir. Thank you sir.
Okay, thank you, ma'am. Any participant has any question, they can ask.
So, madam, I have one question.
Sir,
Is that which method is used in your research work?
melt quenching method, conventional quenching method sir.
Okay, sir. Okay, sir. Another question is that
Sir.
what is the main use of your research work application?
So physical properties of the sodium tetraborate when which are doped with the alkaline earth material. So I have to find out the physical properties.
Okay, sir.
Anybody else
Next
has any
question is that
Sir,
yes, Dr.
can
Ali Ahmed.
you? Okay. Next
sir,
question from other side. You can.
Yes, Dr. Sumit sir, you have any question?
Yes, sir. I have the same question. The applications. What are the applications of your this sodium tetraborate glass?
sir, these
And how they are different from the other particular glasses which are used in that particular application?
actually these are actually which are used in the shielding materials sir, and the solid state batteries also.
Radiation shielding.
Yes.
Okay, so how these glasses are more important than the other glasses already used for radiation shielding?
Actually, this is having the low chemical durability, sir.
Okay,
So, from the literature, I concluded that is also.
right. Done,
So,
sir.
ma'am, actually, how you have tested the low radiation?
Don't know, sir.
Okay, fine. So, thank you so much, ma'am.
Thank you, sir.
Let's thank the speaker for giving a very nice presentation. Now,
Thank you,
our
sir.
next presenter is Mr. Srinivasa Ramlujam sir. Sir, are you? I hope you are available. You can start your
Yes, sir,
presentation.
available, sir.
Yes, sir.
Sir, my screen is available, sir.
No, sir.
Yes, sir. We can see the screen. Please switch on your video.
Yes. Yes, sir. Yes, sir.
Yes, sir. You can start. So,
Okay,
sir,
sir.
again, just to tell you, there is a total time. We are running out of time. There is a total time for around 8 minutes. So after 7 minutes, I put my mobile on the alarm. So after 7 minutes, you'll get an alarm. Within 1 minute, try to wind up, sir.
Okay, sir.
Please start, sir.
So my screen.
Yes, sir. Everything is fine. Please go ahead.
Okay. So, like, I'm going to discuss about the role of molybdenum ion in turning optical and structural behavior of bismuth lead flow bismuth border glasses. Sir, I'm pursuing PhD from Telangana University. So, in the introduction, glass is amorphous solid is having a perfect point. So, there is a like once you're heating the glass, glass first will be getting soft. The glass will first be having a range of temperature, not a sharp melting point. It will be first deformation will start.
Excuse
Then
me,
it
sir.
will
Please
be
move the slides.
okay.
Move
So
the
here
slides. Slides
sir,
are not
I'm
moving,
moving
sir.
the slides.
Now
Slide
it's
is not
okay.
moving, sir.
Now it's okay. Go ahead. Go
Okay.
ahead.
Okay, sir. So, like in the glass section, we can classify it into different types: glass farmers, network modifiers, and conditional farmers, depending upon the material we repair. So, generally, glass are made with bismuth and silicate remain glasses. So, here, when compared with silicate glasses, borate glasses having a low temperature. Uh, they are having low temperature and for this we can we can get a glass and when we add borate we get borosilicate glass. There are much applications and because of their high chemical durability and the thermal shock resistance and like if you take borate and add with the bismuth glasses they are much more useful in like bismuth is a network modifier and it increases density, moisture resistance, and extent IR optical transparency will be increasing. And well, like one, if you take one more oxide like molybdenum oxide, which having a various like multiple valencies from -3 to +3 to +6. So by and one more thing is molybdenum having a high dissociation energy which leads in applications in the fields of electronic like light modulations, high memory devices, and LED and all these shields. And one more application is in the radiation shielding. So because of these properties, and we are using this material which is made with glasses for like studying about the applications as well as the shielding applications also for radiating. Molybdenum is having one more advantage of shielding capability will be increasing. Gamma radiation can be increased by using the molybdenum. Lead is anyway it's a very good shielding material. So in addition to the lead, if you use molybdenum, so with the less concentration of lead also you can increase the capability of the material. And like in this the main purpose of preparing the molybdenum oxide, lead sulfide, and bismuth borate glasses, which having a very small quantity of chromium, and studying the physical, optical, and structural parameters of the glass, and estimate the influence of this different modifiers, like different concentration of the molybdenum in the behavior in the glass properties. And here, for preparing the glass, we have used melt pinch method. So first we have taken all the unagregated reagents, and they are grounded at a temperature of 120. Sorry, for 120 minutes, and then they are used in they're prepared or like we heated them in a furnace at a temperature of around 1000 degrees for about 1 hour, and then the homogeneous molten liquid is taken and pinched in a metal plate at around 200 degrees centigrade, and we have done after that we have kept them in annealing for about 2 to 3 hours so that some stress can be removed from that and we get a stress-free glasses. This is the concentration of the glasses, different composition of the glasses. Like first sample, the molybdenum concentration is very low. As we are increasing molybdenum concentration, the lead concentration was decreasing. And this excited pattern. So the excited pattern confirms that there are no crystalline formation. It's a completely amorphous solid is forming. And then we find out the density of the material by using this Archimedes principle. And with the density, we have found out the molar volume, different molar volume. And oxymolar volume and density of the glass, density and the sample. As the concentration of molybdenum is increasing, as the concentration of molybdenum is increasing, density is having a variable like variation, and whereas the molar volume is decreasing continuously. And this is a graph between oxygen molar volume and the oxygen packing density. So as density is decreasing from 4.7 to 4.6, 4.4. So reason may be due to the density. We are decreasing density of sample, which initially having a larger concentration of lead fluoride. It is replaced by the lower density of the molybdenum. So that's why the density may be decreasing. That's one point we can say. And the decrease in molar volume may be due to MOO3 is replaced by PbF2. So because of that, there may be a decrease in the density of the structure. And the structure, the oxymolar volume of the glasses were decreasing from 16.4 to 13.05 values. These OPD values are changing from 62.33 to 76.62. Oxymolar volume and OPD values are decreasing or increasing because of the structural modification of the glass networks. And the next we have studied about the UV spectroscopy with optical should study the optical properties. We have used the formulas to find out the, like we can see the graph here. So this graph indicates the UV absorption graph of different wavelengths and absorption percentage. And here we are getting the two peaks. For example, it's a sample of PP first sample. Like for every sample, we have find out the values, and these are the absorption peaks at different wavelengths. So like different samples are getting at different values, and here we have found out the corresponding transition values.
So, sir, now the last 1 minute.
Okay, sir, I'm conclude. I will conclude, sir. So we can see the E by Q value is having a very low value from 2.1 to 2.28, so which represents the crystal is on the borderline, having a big crystal structure. And the Raka parameter, which is B, it is less than 1000, which is standard value. It's around, our values are around 753, 568, and 804 is 141, which indicates the shielding. The shielding is the boron shielding is there less. And these are the energy values we have got. The So these are the energy graph to find the energy, and the surface energy, and we can see the energy value is increasing as the concentration of this molybdenum is increasing, and we have found out the surface energy refractive index, molar graph, molar polarizability, and electronegativity and optical basicity of this material, and dielectric constant metallization factor. So the average energy is around 0.66, corresponds to less defects in the crystal which is forming. So because of formation of decrease of non-bridging oxygens. And the refractive index is changing from 2.7 to 2.16. This value also decreasing, decrease in trend we can see. And there is a decrease in the molar refractive index from 26.62 to 25.33. And electronegativity value also changing from 0.512 to 0.56, which is increasing. So which says that the ionic behavior of the glass because the modified network structures. And we can see the a graph between indirect energy gap and the glass structure. We can see that there is a increase in the energy gap and a decrease in the refractive index. So which are all varies inversely. In the refractive index and the energy varies in opposite direction. This is the FTR graph of different samples. So we are getting these are the peaks which are coming at different wavelengths, at different wave number locations, and this is a declination graph of the sample. And we got different peaks from we are taking the FTR graph from 400 to 600 centimeter inverse. So these are the different 420, 580, 680. These are the different locations where we got the peaks. So which indicates the like different ranges, like 400 to 450 indicates BIO bond, and at 500 to 550 indicates lead oxide bond, and MO4 to MOO3 conversion, and 842 indicates MO2 in MO6 units shifting to higher valence. And these are the different like one more peak we got at 1355, and 1416, which indicates the BO tribunal structure and non-bridging of the boron group. And these are conclusions. The density values are found to decrease from 4.7 to 4.4, and it is due to replacement of molybdenum with lead, and the optical bond energy gap, which is decreasing, increasing from 1.9 to 2.1 electron volts with increase of MOT concentration, and the approach energy of is very low, which having a less disorder, and FTIR is unless confirmed that there is a metal cation at coefficient BO3 BO structures. And there are some differences, and I acknowledge our guide, Dr. Harita Madam, Mohan Babu sir, head of the department, Chandrasekhar sir, Nagaraj sir, for guiding me. Thank you.
Okay, thank you. A very good presentation. Anybody from the audience has any question, you can ask. Dr. Sumit sir, if you have any questions, you can ask.
No question, sir.
Okay, just one quick question. Sir, you have written that refractive index and this energy band gap is changing. So what may be the application of your material?
Sir, actually, I'm using this material for shielding, sir, radiation shielding purpose. Sir.
That I understood, but how are you going to test? What kind of test you're going to involve for this?
For which one, sir? Sorry.
For radiation shielding.
Okay. I'm using PhysicsX software, sir. PhysicsX
okay.
Understood.
Understood, sir. Thank you.
Okay, sir.
Thank you so much.
Thank you,
So
sir.
our next presenter, Aruma Sankarva Singh. I hope you are ready.
Yes, sir. Yes, sir. I am ready.
Oh, yes. Please share your PPT and start the presentation. Sir, after 7 minutes, I am putting a alarm for everyone. After 7 minutes, the sound will come, and try to wind up within the last 1 minute. We are, sir, running out of time.
Yes, sir. Is my screen is visible?
Yes, sir. Just put in the slide mode.
Yeah, I'm doing, sir.
Yes, sir. Everything is fine. Please go ahead.
Yeah, good afternoon. I am Dr. Mohammed Singh, Associate Professor in the Department of Physics, Kitan College. It's located in Hyderabad. My title of this paper is Shielding Capabilities of a Borate Oxide, which is doped by the MOO3, where we are using a metal oxides, cadmium oxide and zinc oxides with K2.
Can you start your video, sir?
Okay.
Okay. Thank you, sir.
Should I continue with my video, sir? Okay. No issue. Maybe net fluctuating, therefore that I am on.
Yeah, you continue.
Okay, right.
If you want to off video, then you can do.
Yeah. This is my presentation, which will go in the four ways. So one is introduction, experimental technique, and physical and optical spectroscopy study. The application where I am focusing on radiation shielding application. This glass material, which is fabricated for the purpose of shielding application. Yeah, now this is the introduction where we know that is radiations, nuclear radiations, which are harmful. Where how it is generated means it is some process of radioactive decay where unstable nucleus loses its energy in the form of photon, which is called as a nuclear radiation. And these radiations, which will give various applications. In many applications, we are using these radiations, which are especially medical, nuclear power, and many other applications also we are using that. But these applications, while you are using these radiations, radiations, it will be harmful to our human life. To health risk will be comes. To protect from human body from these radiations, there is a various methods which are using. Traditionally, we are using some concrete surfaces and lead surfaces. But here, there is some drawbacks with this. To overcome these drawbacks, we are going for the some glass materials. And here, the glass materials, which is having a transparency and it is a low cost, where it is effectively radiating, shielding will be using here. Here, we are using a shielding materials like radiation shielding, which is protecting from the gamma rays. The materials which are required, which are having a atomic number, jet material is required. High jet materials are required. Even for not only gamma rays, we can even come with the neutron radiations also we can protect. When we are using radiations which are coming from the neutron, it is a low jet materials we are going to use it. Now, these are the radiation, some traditional shielding materials which we are using as a, here I am showing that is a conventional concretes and lead materials we are using. Lead, it is a harmful where, which is heavy. Additionally, they are heavy and not portable, and there is a toxic is also exist in the LED. Sorry, lead. These and some other traditional materials also which are used, which are alloys, flash asbestos and rocks and marbles, slag and polymers, many things which are used for shielding the radiation. Now, coming to the point where we are using a glass materials. These glass materials which are effective compared to the other materials what we have discussed just now, concrete, lead and other materials. Whereas the glass has a thing which is here, lighter weight and suitable and various applications it is there. That is, I'm showing here the glass materials which are having a transparency, especially in a medical applications, we are using a glass windows, globe boxes and hot shells, we are going to use it. And spectacles, which will be protecting our eyes. And medical applications, we are using a glass vial and syringes, which are also using for the cancer patients, where the doctors which are working under a radiation, gamma radiations they are going to be using. For that, we are using these transparency, especially transparency, low weight, and portably we can carry these glass materials. With the aim of this application, we prepared a glass materials. Now, already our previous presenters are presented that what is glass. I'm not going to talk about that. But here, there is a net farmers and net modifiers we are using. And network farmers which are using in a glass materials. There is a borate glasses which are especially chosen. And in that, when these borate glasses are doped with the network modifiers, we form a strong network which will a glass will be formed. And this borate has a peculiar property where high transparency and low melting and high thermal stability. Because of that, with this material, which is forming a good network with the farmers, and it is glass material will be formed. Along with that, we are going to be add some conditional glass farmers where CDO, ZNO is also added. When we are adding this low concentration, the network modifiers will act as a good network farmers and high concentration. And along with that, there is a heavy metal oxide, which are MOO3, which is molybdenum oxide, which is very useful in a radiation shielding applications. By adding or doping this material, it is a perfectly acting like a shielding material. And now, this is the series which I have used, that the molar concentration of the MOO3 is going to be increases from 0 to 2 mole percentage with incremental of 0.5 mole. Whereas changing with respect to the farmer which I have used, network farmer, which is a potassium oxide. This is going to be reduced simultaneously with the 0.5%, no, 0.0 mole percent of the MOO3. That is K2O3 mole percent is replaced with the incremental of MOO3. And these are the 5 series I have fabricated, which is using a method of melt quenching, which is a traditional method. Everyone knows this. So this is a very simple method where the precursor materials are taken into the braided and grounded in a mortar, and it is these chemicals are taken into the furnace with a 1100 degrees centigrade, and it will be maintained at a high temperatures and heated, and it is maintained at a 45 degrees, and it become a molten, and it is again we have to be taken, and it is mixture with a stable because of to get a homogeneity. Once it is quenched, then it will be form glass, and it will be placed on a quenched on a glass plate which is heating at 100 degrees centigrade. And this is keep it at 24 hours, then we will get a glass sample, and that samples which are having a thickness of 0.5 to 1 mm. And these glasses are taken into the characteristics which are XRD, X-ray diffraction, where we have found this X-ray peaks. There is no sharp peaks, which indicates that it is a good amorphous materials. And after that, studied the density of a glass materials. Here, density it is shown, which is slightly increasing. Where the requirement of the density is going to be increases, which is suitable for the radiation shielding applications. Where we are going to see this, it is density is slightly increasing with the non-linearity, that's 3.47 gram per cc to 3.45 gram per cc with the increment of the MOO3. And also studied the optical absorption spectra, where absorption has noted, and this indicates optical properties are very clearly. Urbach energies plots.
Sir, sorry to interrupt you. Please try to wind up in a minute.
Right. These are the plots which have indicated, and physical properties has calculated, whereas especially density is increases, and molar volume is also increases. Molar value is going to be decreasing non-linearly, and refractive index value it is going to be increases, which is suitable application for the radiation shielding application, and Ubar energy which is also going to be increasing. And this is the application where radiation shielding, especially if you talk about the photoelectric effects are predominant when it is at low energy, and after that moderately it is impact the Compton effect and pair production, especially in the radiation. This is the physics X software I have used. It is a simulation tool where the radiation alpha rays, which are gamma rays, which are going to be fall on a sample. Here I kept it as middle sample, and it is going to be detected once the radiation is passing through the sample, which is going to be detected. This is the simulation setup where we have to be collected the data. In that, the two parameters which are going to be calculated were studied, which is LAC, linear attenuation coefficient. And this is, if you see that the molybdenum doped with potassium and lithium I mentioned, potassium borate cadmium zinc classes. Here LAC is a rapidly incident energy is increases with a small jump of 0.2 MeV. And then the detected peaks is directly proportional to the molybdenum oxide content. And the 0.1 to 4 mega electron volts, there is a Compton effect is predominant. Later, it is a pair production which is going to be dominated. And then MAC is also calculated, which is mass attenuation coefficient. It is the formula it is mentioned, LAC by rho. The rho is the density of the glass material. This is also see the same nature which is going to be observed in it. And here the peaks are which is shown here, the graph which is plotted between LAC and energy. If you see the lower energy state where we are going to see photoelectric effect is dominated after 1 to 4 0.1 to 1 mega electron volts, it is a Compton effect is then, and after later that 4 mega electron volts, there is we are going to see there is a pair production, but it is photoelectric interaction is a predominant at this graph plots which shows where mass attenuation coefficient also it is showing the same nature. Here, higher linear and recorded the lowest end of the energy spectrum during the high interaction of the photons. This is the values which is demonstrated declined interaction probability and hence greater penetration of the gamma rays. These are two characteristics which are studied in a radiation shielding. along using this LAC and mass attenuation quotient, if you know that, then we other parameters also which can be calculated, whereas a half value layer, mean free path, and effective atomic number, effective electron density, equal atomic number, and these also which are very important in how these material shielding the radiations. In that, these parameters will be useful. But majorly we have to calculate it or determined LAC and NAC, which are effectively the MOO3 doped potassium oxide doped borate classes, which are shielding more effectively. That is the conclusion which is conducted in this my research. Thank you.
Thank you, sir. A very nice presentation. Anybody would like to ask any question to the presenter?
Sir, I have one question.
Yes.
How you quench the material, your glass? Is it oil quenching or simple water quenching? What method you have used?
Sir, only that is once we have to remove that material. It's a steel plate we are going to be press on a glass material. Once it is poured into the iron plate with normal room temperature.
That means air, simple air quenching.
Air quenching.
Okay, good. Right, sir.
Okay, sir. Yes, just a one question.
Yes, sir.
Is it possible that we can do the coating of some metal on your material? Have you tried doing a coating like a substrate?
Again, which material it is prepared, and on that we are going to coating.
Okay, let's say, sir, I want a coating of ITU. Is it possible?
Sir, it is not, because of high temperature we are maintaining 1100 degrees centigrade in a furnace. Then it will be not possible when during the quenching. It is a short period of time. We cannot be coating in that.
Okay, thank you.
Thank you.
So our next presenter.
Sir, I'm ready, sir.
Okay, sir, please start. Sir, again to request you that you have a time of total 8 minutes. After 7 minutes, the alarm will give you the signal to wind up.
Is my PPT visible, sir?
Yes, sir. Just put in the slideshow mode.
Is it okay, sir?
Yes, sir. Everything is fine, sir. Please go ahead.
Okay. Good afternoon, one and all. I'm Dr. Ashok Bhogi, Senior Assistant Professor and Head of Department of Physics, VNR Vignan Jyoti, Institute of Engineering and Technology, Hyderabad. My title of my presentation is Optical Properties of Molybdenum Doped Lithium Boron-based Glasses for Potential Optical Fiber Applications. Just a minute, sir. Right. So title of my presentation is Optical Properties of Molybdenum Doped Lithium Boron-based Glasses for Potential Optical Fiber Applications. So outline of my presentation is introduction, experimental characterization techniques, results and discussions, and conclusions. Coming to introduction, I think we know that based on the atomic arrangement, the solids are classified into two categories. They are crystalline solids and amorphous solids. Crystalline solids are the solids in which all the atoms are arranged in the regular manner and the environment about any atom is same. It means that the crystalline solids are having long range periodicity. The crystalline solids are also having extended melting, sharp melting point and anisotropic in nature. Whereas amorphous materials are the materials in which all the atoms are arranged in the regular manner.
Dr. Ashok, I'm sorry, can you just switch on your video?
Just a minute. It's okay, sir?
Yes, sir. Please go ahead.
Right. So here, okay, just a minute, sir. Is it okay, sir, now?
Yes, sir, everything is fine. Please go ahead.
Okay. So outline of my presentation is in, sorry. So coming to introduction, so I think we know that based on the atomic arrangement, the solids are classified into two categories. They are crystalline and non-crystalline solids. Crystalline solids are the solids in which long-range periodicities exist.
Sir, sorry, just click on the slideshow mode.
Yes, it is in slides. Just a minute, sir. Right, sir.
Yes, sir, thank you.
So crystalline solids are the solids which are having the long range periodicity. These crystalline solids are also having extended melting point and anisotropic in nature. Whereas amorphous solids are solids in which all the atoms are arranged in zigzag manner. It means that these solids are having short range periodicity. The amorphous solids are having extended melting point and isotropic in nature. The best example for amorphous solids are glass materials, rubber, plastic, and so on. Among the above, here I'm going to concentrate on the glass materials. I think you know many of the presenters have given the definition of glass material. So glass is an amorphous material and may be defined as a supercooled liquid which exhibits the glass transition temperature. The multi-component oxide glasses consist of glass formers, conditional glass formers, glass network form modifiers, and stabilizing agents. So there are some oxide materials which are the only known glass formers by their own, such as silicate, germanate, borate, phosphate, etc. Some of the conditional glass formers you have mentioned, and they are tellurium oxide, bismuth oxide, vanadium oxide, and molybdenum oxide. The glass network modifiers are lithium oxide, sodium oxide, potassium, calcium, strontium, and barium oxide, etc. The borate glasses are thermally stable. Actually, the borate glasses are thermally stable, moisture resistant, and structural. And and their structural properties also change when the alkali or alkaline earth cations are introduced into them. When with the addition of alkali or alkaline earth oxides like lithium, calcium, strontium, barium to borate, conversion of triangular BO3 units into tetrahedral BO units takes place without the creation of non-bridging oxygens. This conversion leads to the increase in the stability of glass system. Coming next one, glasses containing the transition metal ions give rise to uh, good nonlinear optical properties, high refractive indices, and good chemical durability. And also find various applications in various fields like optical fiber communication systems, laser hosts, rechargeable ion batteries, supercapacitors, photonic devices, photocatalysis, solar energy converters, and gas sensors. The addition of alkali oxides may improve the physical properties of these glasses as well as modify their or improve their preparation conditions. Lithium borobismuth glasses are having good electrochemical properties, long durability, less weight, maximum voltage. Hence, these materials are used as supercapacitor device applications. Molybdenum ions are found in variety of valence states like +3, +4, +5, and +6, which may help to improve the optical, electrical, and electrochemical properties of the glasses. Molybdenum doped borobismuth glasses are having potential applications like rechargeable batteries, supercapacitors, photocatalysis, electroanalysis, and gas sensors. Hence, the molybdenum doped lithium borobismuth glass system is identified for the present investigation. The chemical composition of this glass system is given as 20 Li2O, 10 Bi2O3, 70 - X B2O3, X MOO3. The X values are varied in steps of 0.25 mole percentage up to 1 mole percentage. Coming to experimental, actually there are different techniques have been used to prepare the inorganic glass materials in various forms like bulk glass material, sheet glass material, powder glass material. The following techniques are used to prepare the glassy materials. They are: the first one is thermal evaporation, sputtering, chemical vapor deposition, conventional melting quenching, and salt gel technique. Among the above, in my research work, we have used the conventional melting quenching technique because of the following reasons. The first one is glass preparation and handling are very easy. Second one is speedy preparations of innumerable compositions of glass are possible. Third one is simultaneously we can get both amorphous and crystalline glass materials in the same melt. Next one, large flexibility of composition and flexibility of geometry of glass. Because of these advantages, we have used the melting quenching technique in my present study. So this is the flow chart for the glass preparation. So this is the other side of the flow chart of preparation of glass materials. The starting materials used in the preparation of glass samples are analog reagent grade chemicals of 99% purity. So initially the starting materials are weighed using digital balance with an accuracy of 0.001 grams and grinded to fine powder. After obtaining the homogeneous mixture or fine powder shifted to crucible, and the crucible with the fine powder is placed in the programmable furnace, and the temperature is raised to up to 1200 degrees centigrade, and stirring was done continuously in order to get the homogeneity. So finally the melt was quenched on a brass plate. So after completing the quenching, we will get the glass samples. Then it will be again kept in the another
Sir,
furnace.
sorry to interrupt you. You have only 1 minute left.
Okay, thank you, sir. So here, next one, this is the way to prepare the glass samples. So this is the chemical composition of my glass system. Coming to characterization of glass samples, so I have done four characterizations. One is X-ray diffraction, second one is the same, third one is density, and final one is the UV visible absorption spectroscopy. Coming to first one, X-ray diffraction technique. Actually, XRD works on the principle of Bragg-Law and uses monochromatic X-rays to analyze the samples. So this is the X-ray diffractometer we have used for my sample to test whether the prepared samples have amorphous nature or crystalline nature. So this is the X-ray diffraction pattern of the prepared glass samples. In this X-ray diffraction pattern, no sharp peaks have been observed. The absence of sharp peaks represents that the prepared glass samples are amorphous in nature or non-crystalline in nature. Coming to second one, scanning electron microscopy, the morphological characteristics of prepared glass samples were studied with the help of a SEM. It gives the images with high resolution. In this image, the smooth or homogeneous surface is observed, which is a characteristic of glassy sampler. So that's why, we can say that the prepared samples are glassy in nature or amorphous materials. Next one, this is the IDEX of the prepared glass samples. IDAX is used to know the elemental composition of the prepared glass system. It is used to detect the presence and distribution of elements in the glass system. So here this is the IDAX of the LBBM 1 glass sample. This spectrum reveals that the presence of boron, oxygen, bismuth, molybdenum elemental peaks. Coming to density, the density of the prepared glass samples have been measured with help of Archimedes principle A by A minus B into 0.86 gram per cc. So these are the density values of the prepared glass samples. The density values are increased with increasing the concentration of molybdenum up to 0.75 mole percentage, and later the density value is observed to decrease. It means that the non-bridging oxygens are increased up to 0.7 mole 5 percentage, and later the NBOs are decreased. Coming to next one, UV visible optical absorption spectroscopy. UV visible optical absorption is an important tool to understand the structure of the amorphous materials with various compositions. It is also used to determine various optical parameters like cutoff wavelength, optical band gap energy, and Urbach energy. Actually, the basic principle behind the UV visible optical absorption spectroscopy is Beers-Lambert's law. So this is the Beers law. This is the diagrammatical representation of the Beers law. The amount of light absorbed is proportional to the concentration of the absorbing substance. This is the rate. Beers law represents the rate of absorption, whereas this is the Lambert's law. The Lambert's law represents represents that the amount of light absorbed is proportional to thickness. According to Beers, we can say that the absorption is based on the thick concentration, whereas according to Lambert, the absorption is based on thickness of the sample. So finally, Lambert's law is the amount of light absorbed by the sample depends on the concentration and the thickness of the sample. This is the law. This law is expressed through this equation A equal to log I naught by I. So this is the optical absorption spectra of the prepared glass samples. From this optical absorption spectra, we have measured the cutoff wavelength and cutoff wavelength values of the prepared glass samples. And next one, these are the plots. These are the plots, tau plots of the prepared glass samples. From these
Sir,
tau plots,
sorry, extremely sorry, sir. Sir, please try to wind up.
within half minute, I will wind up, sir. So this is the tau plot of the prepared glass samples. From these tau plots, we have measured the indirect band gap energies. The indirect band gap energies values are decreased with increase in the concentration of molybdenum up to 0.75 mole percent, and later the value was found to be increased. And next one is this is the Urbach energy graphs. So here the Urbach energies are observed to increase with increasing the concentration of molybdenum up to 0.75 mole percentage, and later its value is found to decrease. And coming to various, the most important two parameters, they are the refractive index and numerical aperture. So this is the formula which can be used to measure the refractive index of the glass materials. And here we also determine the numerical aperture. I think you know the numerical aperture is the numerical aperture of an optical fiber can be defined as the light gathering capacity of an optical fiber. It is can be determined by the following relation: Na equal to n into small n into 2 delta whole power 1 by 2. Here n is the refractive index of the glass sample, and delta is the fractional change in the refractive index, and its value is taken as 0.01. So to use these prepared glass materials as a central core medium of the optical fibers, its numerical value should be in the range of 0.13 to 0.5. The numerical aperture values in the current glass system were found to vary in between 0.28 to 0.30. Therefore, these glass materials are very much useful for the central core medium of the optical fiber. This is the conclusion of my presentation. So in actually my prepared glass samples are very much useful to design the central core medium of the optical fiber based on the numerical aperture values. Thank you very much.
Thank you so much, sir. A very nice presentation.
Thank you, sir.
Anybody would like to ask any question to the presenter, please ask.
Hello, sir. I have one question.
Yes, sir.
Dr. Ashok. Sir, what is the melting point of the brass that on which you have quenched your melt?
300 degrees centigrade, sir.
300 degrees Celsius. Melting point of the brass.
Melting point of the brass is above 1500, sir.
1500 degrees C. Okay, and you are furnace at 1200 degrees.
1200, sir.
So there is any chance of the contamination?
No, sir. No, sir.
No.
There is no chance, sir.
Okay. Right.
Thank you, sir.
Right.
Okay.
Santosh, sir.
Yes. So if there are no other questions, we can thank our speaker. Now
Thank you very
next
much,
speaker
sir.
is, yes, sir. Thank you.
Thank you for giving this opportunity. Thank you very much.
Okay. Radhika ji.
Yes, sir.
Yes, Radhika. Ma'am, please.
Yes, Radhika, please, ma'am, please share your screen.
Yes, sir. I share the screen, sir. Sir, is it visible, sir?
No. Yes.
Sir, is it visible?
Yes, ma'am. Just put on the slideshow mode.
Okay, sir. Okay, sir.
No. Yes, ma'am. You can start.
Sir,
Ma'am, again, just to interrupt you, we are running out of the time. So there is a total time of 8 minutes. After 7 minutes, you'll get an alarm. Try to wind up in the next 1 minute. Thank you.
Okay, sir. Okay, sir. Sir, myself, Radhika, research scholar at Department of Physics, Kakatiya University, Warangal, Telangana, under the supervision of Dr. G. Padmaja, madam. Here, my works, the title of my oral presentation is Spectroscopic Properties of Pigmentation on Bismuth borosilicate glasses. And this is the outline of my oral presentation. And this is the introduction of the glass. The glass is an amorphous non-crystalline solid, usually formed by cooling molten oxide mixtures. Silicon dioxide is the main network former that creates the backbone of the glass structure. Other oxides such as boric acid, zinc oxide, sodium carbonate, bismuth oxide modify the properties of melting temperature, strengthens, and optical behavior. By adding rare earth oxides, glass can be engineered for special features, luminescence, and color tuning. Because of these flexible compositions, glass materials are widely used in many applications like electronic sensors and photonic
technologies. There are several types of glasses are present there, sir. Soda lime glass is the mostly common used in Windows and Windows applications. Borosilicate glasses offer high thermal and chemical resonance. Lead and bismuth-based glasses provide high density and refractive index for optical applications. Rare earth doped glasses are used in lasers and photonic devices because they show unique colors and luminescence. In that, we have to study the focus on the bismuth borosilicate glasses doped with the rare earth elements. Borosilicate glasses are the durable, thermally stable materials made from the silica and boron oxide. When doped with the rare earth elements, they show enhanced properties useful for the photonic and the sensing applications. Bismuth borosilicate glasses are known for high density optical transparency and the thermal stability. Bismuth oxide acts as the heavy metal oxide modifier, improving refractive index and nonlinear optical properties. Bismuth oxide and silicon dioxide form a strong glass network. Doping with the rare earth ions by the bismuth borosilicate glasses enhances the pigmentation properties. We study the focus on the pigmentation effect. These are the aims and objectives of my study: to synthesize the bismuth borosilicate glasses with and without rare earth dopants, to study structural, thermal, and optical modification density, band gap bonding, and amorphous nature, to explore suitability for pigmentation and optoelectronic applications. These are the applications of the study: optical devices and sensors, luminant materials for LEDs and display coatings, high density radiation shielding glasses, photonic laser hose, and pigmentation based decoration glasses, glasses for nonlinear optics due to high bismuth content. And this is the preparation of the glass. Here we choose my glasses are synthesized by the melt pinching method. And in that method, raw materials weighted according to the molar composition, mixed thoroughly using the Azenta mortar, and those are melted in platinum or aluminum crucible at the temperature range of 900 to 1100 degrees centigrade, depending on the bismuth content. And homogenized melt poured onto preheated steel plate, annealed here transition temperature, that is up to 250 degrees centigrade to release the internal stresses. Samples cut and polished for the characterizations. We can characterize the samples like XRD and FTI are UV visible. And these are the physical parameters that can be characterized by the samples. And these are the physical parameters of my synthesizer samples. By observing this density and molecular weight increases because of the rare earth oxides, heavier atoms form the packed structures. When these replaced by the lighter ions like silicon dioxide, the total mass of the glass network is denser. By observing the table, without the doping, the density is 6.44 grams. After doped with europium, 6.49 approximately, and doped with samarium, 6.55 grams per centimeter cube density we can observe. Easily we can understand that the density will be increases by adding the rare earth ions, and also average molecular weight also increases by adding the rare earth elements, and molar volume must be decreases. And this is the XRD diffraction pattern for my synthesizer samples. And here this one is the undoped glass sample, and the second one is doped with the europium, and this is the doped with the samarium. And by observing this analysis, all the compositions exhibit the broad holes in between the 25 to 35 degrees, and so it confirms the amorphous nature of the sample. There is no sharp peaks in that pattern. So the rare earth doping does not include the crystallization. And this is the absorption spectra. We analyze that for my 3 samples. In that we can observe the broad absorption in the UV range, that is near 284 nanometer. These are in the visible range, and it can be concluded by, it should be point out that the absorption peak is 284 nanometer is due to the host glass. The absorption spectra in visible region is near 400 to 800 nanometers. The absorption of light in the blue-violet region and red region 620 to 700 nanometer. As a result, rare earth doped glasses is colored slight red, pink or tint of samarium, yellow, orange of slight red or pink europium, yellow, orange tint as samarium. And this is the observation analysis that can be observed here. UV absorption is non-doped glasses is up range is 300 to 350, and the europium doped glass is around 394 nanometers, and samarium glass is around 360 to 400 nanometer range. And here the pigmentation effect shown by the undoped glass is very low, and the europium doped glass is medium, and the samarium glass is high. And this is the FTR spectroscopy analysis data for my 3 samples. And here we observe that the Vi bismuth oxide absorption bands are in between 400 to 450. Yes, this is.
Ma'am, sorry to interrupt
analysis.
you. Please try
Yes.
to wind up in a minute.
Okay, sir, this is the FTR spectral analysis. In that, we can observing that the vibrations, BIO vibrations and the BOB vibrations must be slightly shifted by doping the rare earth elements. These are the conclusions of my study. All glasses are amorphous, dense and thermally stable. Rare earth doping modifies its optical and structural behavior. Europium and samarium improve the pigmentation and luminescence features. These are the suitable for optical, photonic and decorative applications. These are the some differences that can be literature for my work. And I sincerely thanks to organizing committee at first. And I thanks to the RUSA 2.0 for financial assistance through the fellowship. And my special thanks to the organizers and my supervisor, Dr. J. Padmaja Madam. And thank you. Sir, come.
Thank you so much, madam. It was a very nice presentation. Any participant has any question, please feel free to ask.
Thank you, sir.
Okay, ma'am, can you just go to your third slide, slide number 3?
This one, sir?
No, after this, the next slide after this. No, the next to next. After this, the next slide. Yes. See, I just wanted to understand that you have determined the band gap.
Yes, sir.
And the bonding and the amorphous in nature, right?
Yes, sir.
So what do you feel? What may be the future applications of your material?
Sir, these are some.
So you have written the pigmentation, right?
Mainly focuses on the pigmentation applications. Sir.
Okay.
Okay. Sir.
Fine. Thank you.
Thank you, sir.
So the next presenter is Pradeep Kumar G1 0019. As he's not replying, the next presenter is Prajakta Patil G2 0002. Yes, ma'am. Prajakta ma'am, you can share your screen and you can start the presentation.
Hello, sir.
Yes, ma'am. Yes, ma'am. I can see your slides and you are audible. Please start your presentation.
Yes, thank you, sir. I am Prajakta Patil from Devchan, Department of Physics, Devchan College, Arjun Nagar. My topic of presentation is evaluation of spot size of lowest order Bessel Gaussian laser beams in plasma with relativistic ponderometer nonlinearity. My outline of presentation is introduction, objectives, hypothesis, theoretical considerations, governing equations, computational result discussions, and conclusions. In introduction, the phenomenon of self-focusing of laser beam in plasma is an induced lens effect. It results from wavefront distortion inflicted on the beam while traversing a plasma. The distortion is similar to that imposed by a positive lens. Self-focusing is a typical type of non-linear phenomena that depends significantly on the transverse profile of the input beam. It plays vital role to affect other nonlinear phenomena in laser plasma interaction. Several approximate analytical models of self-focusing in plasma were proposed. One of these models, paraxial approach, has been well developed and grounded. Objective is to study the phenomenon of self-focusing of lowest order Bessel Gaussian laser beam in plasma by employing a paraxial approach. Second, to set up nonlinear beam width parameter differential equation to study propagation characteristic of Bessel Gaussian beams in plasma. Third, to solve the nonlinear beam width parameter differential equation numerically. Hypothesis of this topic is by controlling the wave parameter mu in the field profile of Bessel Gaussian beam, it would be possible to control the self-focusing effect in plasma. This is the schematic diagram of a self-focusing phenomena of self-focusing of a laser beam. Theoretical considerations. The Bessel Gaussian laser beam have electric field equations. Electric field distribution of Bessel Gaussian beam is equal to E0 J0 into mu r divided by root 2 r naught into exponential of r square by r naught square, where J0 is the zeroth order Bessel function of first kind, r is the transverse distance from propagation axis, E0 is the amplitude of electric field, and mu is the transverse number of J0 Bessel mode. Figure 2 is Figure 2 is a three-dimensional transfer initial intensity profile of lowest order Bessel Gaussian laser beam for different values of mu, which is transverse component of wave parameter. Mu is equal figure A is for mu is equal to 0, figure B is for mu is equal to 5, figure C is for mu is equal to 10, and figure D is for mu is equal to 15. From figure, it shows that for mu is equal to 0, the Bessel Gaussian beam becomes a normal Gaussian beam, bright at center and smoothly fading outward. Next, we can see that for figure B, C, and D, as mu increases, central's bright spot becomes narrower and more circular rings appear around the center, and energy shifts from center to rings. This is about figure 2. The dielectric function is plasma is characterized by dielectric function, which can be general expressed as epsilon is equal to epsilon 0 plus phi E star, where epsilon and phi are the linear and non-linear part of the dielectric functions respectively. Epsilon 0 is, which is linear part, is equal to 1 minus omega p square by omega square. For plasma induced a weakly relativistic Pondermetrian nonlinearity. Nonlinear dielectric function phi is written as phi E star is equal to omega p square by omega square into 1 minus 1 upon gamma exponential minus m naught c square by t gamma minus 1. And this is the equation 5 is wave equation for electric field, which is del square E plus omega square by c square epsilon E is equal to 0. Equation 6 is parabolic equations 2 ik dou A by dou z plus del square perpendicular a plus k square epsilon 0 phi e star. And coupled equation is solving all above the equation, we get coupled equation 2 into 2 dou s by dou z plus dou s by dou r square is equal to 1 upon k square a naught into dou square a naught by dou r square plus 1 upon r dou a naught by dou r plus phi a naught square epsilon 0. Following all the calculation, I referred approach by Sodha in 1976 for nonlinear differential equation for beam width parameter f for lowest order Bessel Gaussian beam, and we get a differential equation using pondermative nonlinearity as I discussed earlier. D square f by d zeta square is equal to 1 plus mu square by 2 f cube minus rho square omega square alpha e naught square square divided by 2 f cube 1 plus alpha e naught square by f cube raised to minus 3 by 2 into 1 plus mu square by 4 psi. Here rho is rho naught omega by c, dimensionless beam width radius. Omega is omega p by omega p is normalized plasma frequency parameter. Alpha e naught square is the intensity parameter, and zeta is z by k r naught square is the dimensionless distance. And this is the equation for psi, which is given in equation 8. Putting initial condition in equation number 8.
Prajakta ma'am, sorry to interrupt. Now you have last 35 minutes. Sorry, 35 seconds. Please try to wind up at the earliest.
Okay,
Less
sir.
than a
This
minute.
is the critical condition. F is equal to 1, df by d zeta is equal to 1. Putting this equation, we can plot this critical curve. This is critical curve for A is for plasma electron plasma temperature 20 keV, and red curve is for 80 electron plasma temperature 80 keV. And we plotted here two representative point. From this point we can we showed this figure variation of beam width parameter f with a distance of propagation zeta with that two representative point. From this it is observed that for a is equal to 0.3 comma 5 the beam defocuses because it is the point is below these two curves, and b 0.3 comma 11.8 two beams are self focuses A and B because this representative point is above these two curves. Conclusion. In conclusion, the propagation of lowest order Bessel Gaussian laser beams through plasma described by relativistic pondermative nonlinearity is studied. By using the paraxial approach for self-focusing of a laser beam in plasma, we were able to establish the nonlinear differential equation for beam width parameter of the lowest order Bessel Gaussian beams in plasma. The following important conclusions are drawn in the present analysis. The transverse component of parameter mu of Bessel Gaussian beams offers an extra degree of freedom to study propagation characteristics in plasma. Second, stronger self-focusing of Bessel Gaussian laser beam is observed for higher order values of plasma temperature T. Thank you, sir.
Okay, thank you so much, ma'am. A very nice presentation. Any participants has any question, you can ask to the presenter. Okay, ma'am, there is a one question that I have. You're using a computational study. Are you also planning to do some kind of experiment like a rotating plasma?
Yeah,
or the pulse beam plasma?
in future, because I am a first year PhD student, so I haven't think about that. But in future, I will try to do that.
Okay. Thank you, ma'am.
Thank you,
So-
sir. Thank you so much, sir, for giving me this opportunity.
Okay. So our next presenter is Srija KV. Ma'am, kindly share your
Yes, sir.
PPT and start the presentation.
Okay, sir. Is it visible?
Yes, I can see, just put on the slide mode. Yes, ma'am, you can
Yeah,
start.
no, it is. Okay, sir. Good afternoon, sir. I'm Shrija KV from Government College of Engineering, Kannur. I'm here to present a topic, laser-induced breakdown spectroscopy as a tool for the detection of trace elements in sweat. So here is the overview of my presentation. So sweat is a transparent biofluid with a low tonicity and slightly acidic nature with a mean pH 6.3 that is more acidic than blood. Then what are the significance of studying sweat or sweat analysis is that it contains electrolytes, metabolites, trace elements and biomarkers. So it is a non-invasive method, is easily accessible, provides insight into health, hydration and metabolic activity. And the merit of sweat as a biofluid is particularly important in doping and role, that is for testing athletes for banned substances. Due to the presence of very nominal impurities, it can be preserved for a long periods. The applications of sweat analysis that medical diagnosis and health monitoring, detection of dehydration and electrolyte imbalance, forensic application including trace element analysis, sports science and performance monitoring. And among this, we are concentrating on trace element detection. So the excretion of essential trace elements like sodium, potassium, chlorine, magnesium, etc., have significance in the case of nutrition and consideration and heat stress. The excretion of non-essential or toxic trace elements have toxicological and therapeutic importance. And air, soil, water, and food are the major routes through which toxic elements can enter and bioaccumulate in the body. And mercury, cadmium, lead, chromium, and metal oxide, like arsenic, are generally exhibiting biological toxicity. And this will accumulate in our body by forming complexes. So it can be used for heavy metal assessment with some metals occurring at higher concentrations in sweat compared to blood and urine. And it acts as a means for detoxification. And these are the some of the methods used for can be used for sweat analysis. And even though these techniques have many advantages, this will have some disadvantages also. And that is, these are expensive or require highly skilled laborers or less sensitive. And some of these will require samples in liquids form, etc. So we go for laser-induced breakdown spectroscopy for the analysis of sweat. LIPS is an optical emission spectroscopic technique which use an intense laser pulse for ablating the sample, which creates a plasma plume. And the emitted light from this plasma, like any other spectroscopic techniques, when the excited particles, when move to lower energy state, they will emit radiation, which will emit the respective radiation. Means we can identify the elements by comparing the wavelength. The advantages of LIPS techniques is that it require no or minimal sample preparation, non-contact analysis possible, and it's minimally destructive, standoff analysis possible, and it can work in different environmental conditions and atmosphere from air to vacuum, and it is portable. And both qualitative and quantitative analysis are possible with the LIPS technique. And normal collection techniques for sweat sample are direct collection from the skin using so tube, made to measure collection devices such as sweat pouches, glass pipettes, and arm bags. And commercial sweat collection products are available for standardized sampling. But for laser-induced breakdown spectroscopy, the collection of sample is very simple. So we used Wattman grade 1 filter paper for collecting this sample. And the samples are collected from volunteers after obtaining their informed consent. And normal hands without any vigorous exercise were collected for analysis. And this is the experimental setup used in the laboratory. We used Q-switch neodymium lag laser of fundamental frequency 1064 nanometer. Then the focused laser beam is focused with a lens having focal length 10 centimeter onto the sample. And we used an XY translation stage for the easy movement of the sample. And the emitted plasma were collected using two lenses. One is for collimating the beam and other is for focusing the beam on to the edge of an optical fiber cable for collecting this, and then it is connected to a portable spectrometer which also contains a CCD detector, then to the system computer for analyzing the spectrum. Here's the resultant discussion. Here the spectra obtained using laser-induced breakdown spectroscopy, and we selected the wavelength 200 to 800 nanometer. Then the elements are identified by comparing their intensity or the wavelength with the NIST spectral database. And through this method, we could identify the elements magnesium, calcium, sodium, chlorine, nickel, and potassium. And for a confirmation test, we used EDX, and EDX also confirmed the presence of these elements in the sweat samples. And conclusions and future scope. In this work, sweat samples are collected with Wattman filter paper grade 1, and LIPS could successfully identify the sweat elements, normal sweat elements in the samples. So this can be used for identifying toxic elements or heavy elements if the samples are available. And the analysis was found possible with a normal small amount of sweat, and lip saves analysis time. So this can be used for real-time detection of elements, especially heavy metal elements for forensic and clinical purposes. Again, this can be used for the quantitative lips can be used for determining the concentration of elements secreted in sweat, which will be useful for healthcare, sports, and forensic applications. Thank you, sir.
So thank you so much, ma'am. You have done well in time. So any participant has any doubt, any questions, you're free, you can ask. Ma'am, what I can understand is it's a very good study. Like, are you planning for doing some kind of a hydrophobic arrangement for the sweating effect?
No, sir. No, sir. We
Okay, you are not doing.
directly collected the sweat, and after drying the filter paper, it can be directly used in the lip setup.
Oh, okay. Thank you so much.
Thank you, sir.
So our next presenter is Dr. Jayanta Das, H10001. Hope you are ready, sir.
Hello, sir. Am I audible?
Yes, sir, you are audible. Not right now.
Hello?
Sir, yes, sir, I can hear you. Please share your PPT.
Okay.
Yes, sir, I can see your PPT. You can start. And sir, there is a request that after 7 minutes, that alarm will ring. Try to wind up in the next 1 minute.
Okay. Thank you, sir. So good afternoon, everyone. Myself, Dr. Joyantu Das from the Department of, I'm an assistant professor from the Department of Physics, Panchakot Mahavidyalaya, which is situated in West Bengal. The topic that I'm going to present in this session is thickness and stoichiometry dependence of nil temperature of antiferromagnetic nickel oxide 001 film. So basically what I did, I studied the nil temperature variation of nickel oxide thin film, which is an crystalline film, and I studied the nil temperature variation of that film with thickness and stoichiometry. This is the outline of my talk. So first I'm going to explain why I chose nickel oxide, then the thickness dependence studies, and at the last I will discuss the stoichiometric dependence. So why nickel oxide? Because nickel oxide, bulk nickel oxide, it is a prototype antiferromagnet as we know, with the nil temperature 523 Kelvin. That means at room temperature, it is a stable antiferromagnet. And moreover, nickel oxide has a relatively simple structure. It has a interpenetrating sodium chloride structure, interpenetrating FCC structure it has. And as you can see, the alternating nickel up and down spin, the planes, they are arranged in such a way that nickel oxide has the antiferromagnetic direction, which are the one-on-one directions. So in nickel oxide, bulk nickel oxide, you will find there are 4 such antiferromagnetic directions and corresponding 4 antiferromagnetic domains, which are called the twin domains, the T1, T2, T3, and T4. These are the twin domains of nickel oxide. And if you look at the structure and the magnetic structure, you will find that in nickel oxide, the magnetic, because of the antiferromagnetism, the antiferromagnetic ordering of the nickel moments, the magnetic cell is double than that of the crystalline or structural cell. So as a result, since this happens in the real space, as a result of this, in the reciprocal space, you can expect the appearance of some extra lattice spots. That is, the extra lattice spots should come because of the doubling of the unit cell. And if you grow nickel oxide thin film on top of suitable substrate, in our case, we have grown the nickel oxide thin films on top of silver substrate, silver 001 substrate, because it matches very well the crystalline, the lattice constant matches very well. It is only 2% lattice mismatch, and it grows pseudomorphically. So with MB, the molecular beam epitaxial method, we have grown such thin films, nickel oxide films on top of silver 001. And here also, because of this doubling of the magnetic cell, we can find the appearance of 1/2 and 2/1 reconstruction in the nickel oxide thin film. And if we look at the lead, the low energy electron diffraction pattern, in situ lead we find, because of this, as I said, that in reciprocal space and in reciprocal lattice, you should expect the appearance of some extra lattice spots. So these lattice spots actually in the diffraction, you will find as the fractional order spots, the half, 0, 0, half. These are called the half order spots. So in addition to the Coulomb Coulomb scattered lead spots, the 1-0 spots, you can find the additional magnetically exchange scattered half order spots. And what we did, we studied the intensity variation of these half order spots, and from there we determined the nil temperature, and we studied also the nil temperature variation. And moreover, what we did, we utilizing these half order spots, we did with the help of LEAM, the low energy electron microscopy, we have already probed the antiferromagnetic twin domains of nickel oxide, but that's a different story. The thickness dependent studies first I will discuss. So when we did the low energy electron diffraction and we looked at the half order spots for starting from the 1 monolayer to the up to the 15 monolayer film, that means the thickness variation, we observed the existence of this half order spots almost in all the cases except in the case of 1 monolayer film. For to get the half order spots in case of 1 monolayer film, we have to cool down the sample with liquid nitrogen. And as you can see, the result of the experiment done on a 15 monolar nickel oxide film, you can see that at room temperature you can find the half water spot. These are the half water spots, and at when we heat up the sample, when we elevate the temperature, this half water spots vanishes because the sample crosses the nil temperature. So the sample transits from the antiferromagnetic to the paramagnetic phase. So similar studies we did the temperature dependent half water intensity variation we studied for the case of 2, 6, 10 and 15 monolar film, and we observed a gradual this is the intensity variation with temperature, and we find that the intensity completely diminishes at different temperatures. So we observed from 15 to 2 monolar, we observed a gradual decrease of the nil temperature of the sample. And a beautiful thing happens when we go to below the monolar range. Within the submonolar range, we find that the nil temperature does not decrease that much. However, there is an intensity variation at lower temperature. As I said that below 1 monolar and also at 1 monolar, I had to cool down the sample with liquid nitrogen to observe the half water spot. So you can see that while we are cooling down, we can find out some intensities, and we find that the variation of the half water's intensity is there. It depends on the most probably on the domain size of the nickel oxide film. And then the stoichiometry dependence studies. So we did the stoichiometry dependence by heating the sample with argon ion, bombarding with the sample, and as we know, this argon ion energy with 600 electron volt with on the range of 600 electron volt, and when they impact the sample, it the result of the impact is the reduction of oxygen from the sample. So we can create a oxygen to nickel stoichiometry variation with the argon ion bombardment. And as we can see that as a result of the argon ion bombardment, in the integer order spots, we can see the spot size and intensity both changes because of the crystalline ordering variation. And when we did the XPS studies, the X-ray photoemission spectroscopic studies, we also find that with higher bombardment, let's say from 0, this is the result of 0 minute, that means the as deposited sample, then the argon ion bombarded sample for 5 minutes, 10 minutes and 15 minutes, we can see a small tail that gradually rises up, this A prime peak that gradually rises up. This corresponds to the nickel peak. That means the sample, partially there are some metallic nickel, it appears with the argon ion bombardment, and there is an oxygen reduction. So when we quantified, we find that almost 13% metallicity we can get upon argon ion bombardment.
Sir, sorry to interrupt you. Please try to wind up in a minute, sir.
Okay, sir. And when we did this the lead studies with temperature variation, we could observe the half water intensity variation with temperature, and we could quantify, we could determine the Tn values for these samples. And as you can see, these are the first, second, third, and fourth sputtered. I mean the argon ion sputtered and sample, and they are the results I am showing. And when we oxygen anneal the sample, and we can get back the similar result as the as prepared film. So this stoichiometric and the stoichiometric variation, it can recover itself with oxygen annealing. So these are the studies. These are the two studies I am showing. I have shown. One is the temperature dependent Tn variation, and another one is the thickness dependent variation. So all these studies were done at the Saha Institute of Nuclear Physics, the angle result photoemission spectroscopy laboratory, and we used the in situ film deposition and quantification facility there. These are some of my publications related to the topic, and thank you so much.
Thank you so much, sir. It was a very excellent talk, very informative within the time whatever was given by this organizing committee. Anybody has any thing that we'd like to talk to Dr. Jayanta Das, please feel free to ask him. So, sir, as I cannot see any questions, thank you so much on behalf of this entire organizing committee for an excellent.
Thank you for providing me the opportunity to present the paper here. Thanks a lot, sir.
So, as I cannot get any kind of a response from Dr. Vipin Kumar.
Sir, myself available, sir.
Okay, sir, then you can start your presentation, sir, please.
Okay, sir. Okay, sir. Is my PPT visible, sir?
Yes, sir. We can see the slides. You can start, sir. Okay, sir, after 7 minutes, the alarm will going to ring. Please try to wind up in a minute.
Okay, okay, sir. Okay. Thank you, sir. The topic of my paper is sol-gel-derived screen-printed AL-doped ZNO film preparation, characterization, and optoelectronic applications. The abstract of my paper is the fabrication of AL-doped ZNO with AL 0.05 film was achieved through a simple and cost-effective solved method associated with the screen printing. The structural and optical features of the fabricated film were investigated via X-ray diffraction and UV visible spectroscopy techniques, respectively. XRD analysis confirmed that the nature of the film is polycrystalline, featuring a hexagonal structure. The optical bandgap obtained from UV visible spectroscopy and was established. The bandgap was found to be 3.35 electron volt. The electrical characteristics of the film were examined using Hall measurement, revealing that it exhibits a N-type conductivity with a low resistivity of approximately 1.02 into 10⁻³ ohms into centimeter. These outcomes collectively suggest that AL-doped ZNO films can be effectively used in industrial production for optoelectronic devices. The introduction. Zinc oxide is among the most cost-effective and budget-friendly materials. It is a direct bandgap semiconductor exhibiting N-type conductivity with a bandgap of 3.37 eV. For the purpose of enhancing its electrical and optical features, ZNO film has been doped with multiple metals like copper, Ag, Al, tin, and indium, etc. Al doped ZNO films by combining the sol-gel method with the screen printing method. The experimental details: step 1, zinc acetate 95% plus aluminum chloride 5%. Step 2, MEA was added as stabilizer and ethylene glycol was used as binder. Preparation of gel. The prepared gel was screen printed on the glass substrate. The prepared films were firstly dried at 120 degree for 30 minutes and then finally fired at 500 degrees centigrade for 15 minutes, and followed by the characterization through XRD, optical and electrical characterization. The structural results: XRD peaks at 31.85 degree, 34.55 degree, and 36.30, 47.50 degree, and 56.60 and 62.85 degree, resembling with the JCPDS file number 361451 and showing the hexagonal Woodjard structure. Polycrystalline nature with 101 preferred orientation. No secondary phase detected. Al ion is well integrated into the ZNO lattice. Mean particle size wise about 50 nanometer. This is our XRD pattern of our film. And now the optical analysis. Optical transmittance in the range of 300 to 900 nanometer. Bandgap were calculated through the Toc relation. Bandgap was found to be 3.35 electron volt, aligning with the bulk ZNO, suggesting incorporation of aluminum ions into the ZNO lattice influences the confinement. This is the transmittance spectra of our film, and this is the Toc plot by which we calculated the bandgap equal to 3.35 electron volt. Electrical analysis. By Hall effect measurement, the deposited film possesses a resistivity of 1.02 into 10⁻³ ohm into centimeter, a mobility of 24.5 centimeter square into second, a carrier concentration on the order of 10⁻20 centimeter minus cube substitutional incorporation of aluminum ions on the zinc sides. Conclusions: Zn 0.95, Al 0.05 film O film on glass substrate using the sol gel associated with the screen printing. Pure hexagonal Woodjide structure confirmed by XRD. Band gap through the optical results found to be 3.35 electron volt. Low value of resistivity 1.02 into 10⁻³ ohm into centimeter. Suitable for optoelectronic devices. This is the acknowledgement. The authors sincerely express their gratitude to Dr. Manoj Goyal, Executive Director, and Dr. Adesh Kumar Pandey, Director Academics, Kite Group of Institutions, for their invaluable support and encouragement throughout the course of this work. These are few references, and thank you.
Thank you so much, sir. A very good presentation, very informative. So any participants has any questions, you are free to ask to Dr. Vipin Kumar. Dr. Sumit, would you like to ask anything to Dr. Vipin Kumar?
Dr. Sumit has any meeting this time.
Okay.
So he will join again for 15.
Okay. So, Dr. Vipin Kumar, I have one quick question to ask. That as you are working on the ZNO and you have doped aluminium, right? So aluminium is basically a kind of a conducting a metal.
Yeah.
Right. Are you also planning to dope and making a core shell kind of a structure with the aluminium?
No, sir, we are not planning core type structure right now.
Okay. Okay, sir. Thank you.
Okay, sir. Thank you, sir.
So we can request our next presenter to start. Dr. Anirudh R. Sir, are you there in the meeting? Dr. Anirudh R., are you there in the meeting?
Yeah, he's in meeting.
Okay.
Dr. Anup, please share your screen.
If you are not there, I can request Mr. Srijit P. H1 0004 to present. Mr. Srijit, are you there in the meeting? Okay. Yes, you can start. You can start your presentation. After 7 minutes, you'll get alarm. Then let's try to wind up in a minute. Sir, we cannot hear you. You are not audible, sir.
Okay, sir. Can I audible?
Yes, sir. You are audible now. You can start.
Good afternoon. My name is Srijit P, Assistant Professor, Department of Physics, Malabar Christian College, Kozhikode, Kerala. The work presented here was carried out at the Solid State Physics Laboratory, Department of Physics, Cochin University of Science and Technology. In this presentation, I will discuss the preparation, structural and optical and electrical studies of copper sulfate and indium sulfate thin films and the fabrication of a PN heterojunction diode on a FTO substrate. Compound semiconducting sulfide thin films are of significant interest due to their applications in optoelectronic devices such as photodetectors, solar cells, and sensors. Indium sulfide is an N-type semiconductor with a wide band gap, while copper sulfide is a P-type semiconductor with good electrical conductivity. The combination of these two materials makes them suitable for heterojunction diode fabrication. Fluorine-doped tin oxide or FTO was chosen as the substrate because of its high transparency and good electrical conductivity. The thin films were prepared using the reactive evaporation technique employing Gundur 3 temperature method. In this method, the metal source, sulfur source, and substrates are maintained at 3 independently controlled temperatures. This allows precise control over the sulfurization process and ensures stoichiometric film growth. This technique is particularly suitable for sulfide thin films due to its ability to produce high purity and well-controlled compositions. To summarize the methodology, we initially optimized the vapor deposition parameters including pressure, temperature, and time. The thin films were then deposited and characterized using electrical, optical, and structural techniques. Based on these optimized conditions, a PN heterojunction diode was fabricated and its performance was analyzed. By carefully adjusting the deposition parameters, indium sulfide thin films with different stoichiometries were obtained, namely INS, IN2S3, and IN2.77S4. Similarly, optimized copper sulfide thin films were prepared. These variations in stoichiometry significantly influence the structural and optical properties of the films. Based on these studies, IN2S3 and CUS were selected as the most suitable materials for heterojunction fabrication. X-ray diffraction studies confirmed the crystalline nature of the deposited films. The observed diffraction peaks matched well with the standard JCPDS data, confirming phase purity. Energy dispersive X-ray analysis further verified the elemental composition and near stoichiometric ratios of indium, copper, and sulfur in the films. These results confirms that films are suitable for device fabrication. FESM was used to study the surface morphology. FESM images of IN2S3 films show uniformly distributed grains with a compact structure. COS film exhibit characteristics clustered grain morphology. The absence of crack or pinholes and the uniform grain distribution are essential for good interface formation in heterojunction devices. UV visible NIR transmission spectra were recorded for all thin films. The optical band gaps were determined using top plot. The band gap values were found to be 2.09 electron volt for IN2S3 and 1.883 electron volt for CUS. These band gap values indicate that the materials are suitable for optoelectronic applications. Spectroscopic elysometry measurements were carried out and analyzed using CompleteEase software. From the elysometric data, the refractive index and extinction coefficient were extracted. Ellipsometry analysis of the bilayer structure yielded thickness of approximately 150 nanometer for IN2S3 and 100 nanometer for CUS, confirming uniform film growth. The SEM images shows that both IN2S3 and CUS thin films exhibit a uniform surface morphology. When CUS is deposited on IN2S3, a continuous and uniform surface is formed, confirming good interfacial coverage, which is essential for effective heterojunction formation. Based on the structural and optical results, an N-type IN2S3 layer was deposited on the FTO substrate, followed by a P-type CUS layer. Care was taken to ensure clean interfaces and proper contact formation, which are crucial for achieving good diode performance. Current voltage measurements were carried out to study the electrical behavior of the heterojunction. The IV characteristics show clear diode behavior with low reverse current and an exponential increase in the current under forward bias. This confirms the successful formation of an IN2S3 PCUS heterojunction diode. In conclusion, stoichiometrically controlled indium sulfide and copper sulfide thin films were successfully prepared using reactive vacuum evaporation. Structural, optical, and morphological studies confirms the high quality of the films. The fabricated PCUS and IN2S3 heterojunction FTO exhibits good diode behavior, demonstrating its potential for optoelectronic device applications. I would like to express my Sincere gratitude to my research guide, Professor B. Pradeep, Department of Physics, Cochin University of Science and Technology, Kerala. I would like to thank the organizers of the ICC India 2025 conference for providing the opportunity to present our research. Thank you all for your kind attention.
Thank you so much, sir. It was a very nice presentation. Any participants would like to ask any question to Srijit, please feel free to ask. Sir, can you go to the slide number 7?
Okay, sir. Okay.
Yes, sir, like you have said that you have uniformly grain IN2SO3 films.
Yeah.
So that you have done FESM, right?
Yeah.
I cannot see the size that is there. Maybe.
Okay, I can zoom the.
No, you can just tell me what was the size that you have got.
You
can just tell me orally. No, not a problem.
The indium, the size is about 50, I think.
50 nanometer.
Nanometer. The CUS films, the length is 150 nanometer. And the width is 50 nanometer.
Okay, fine. Okay, sir. Thank you. So our next presenter is, yes, sir.
I have one question. Why are he's using indium actually? Indium is, this is not good. Of course, it is available, but for future application, it is not good. Hello. Is it visible? Can you hear me?
Okay, sir.
So indium, you are using indium. So indium is for solar cell application, for any application, actually, we are not supposed to use indium.
Instead of cadmium, the indium is a good choice.
Cadmium is non-toxic. It is toxic material, so we are not supposed to use cadmium. But indium also, is rare material.
Yeah.
For commercialization, it is not acceptable.
Okay.
So try another material, then is good.
Okay.
But your work is very good, simple but effective.
Okay.
Thank you.
I think Dr. Anurup R is again joined again.
Yes, sir. You, Dr. Anurup R, you can just present your slides. Yes, you can and start your presentation.
Yes. Am I audible, sir?
Yes, sir.
Am I audible, sir? Okay.
Yes, sir. You are audible.
Okay.
Dr. Santosh sir, can you announce the name of absentees in this session?
Yes, sir. Already I have put in the chat group. I will also announce.
Is this last presentation?
Yes, sir. The two presenter, M. Sripat and Chinta Madhu Babu, they were not present.
Okay, sir.
So again, I'm putting on the WhatsApp group.
Session, right? Okay.
Santosh, can you confirm that the absentees?
Yes, sir. I'm just putting again the message in the WhatsApp group. On this chat, sir.
Okay.
Sir, please start. Dr. Anurup, please start.
Maybe he has internet problem.
Sir, you can stop your video and just you can present your slides. Dr. Anurup, you can stop your video and you can just present your slides.
Sir, I am audible.
Yes, sir, you are audible. I think there is some network issue from your side. So better you need not switch on your video. You can just start your presentation, sir.
Okay, sir. Thank you. Sir, is it visible now?
Yes, sir. Everything is fine. Please go ahead, sir. Just put on the slideshow mode and then you start your presentation.
Yes.
Yes, sir. Please go ahead. So after 7 minutes, you'll get an alarm. So try to wind up in a minute.
Good afternoon, all. My name is Dr. Anurup R. I am from the Department of Physics, Baby John Memorial Government College, Kollam. The topic of presentation is an investigation on the properties of IN4SE3 copper Schottky diodes fabricated by reactive evaporation on FTO substrates. First of all, introduction to chalcogens and the chalcogenates. Elements in group 16 of the periodic table are called the chalcogens. The name derived from the fact that they are ore formers. They exhibit a common oxidation state of -2. The compounds of chalcogens are called chalcogenates. Then binary and ternary chalcogenates are widely used in optoelectronic and thermoelectric devices. Here I am going to present about a binary chalcogenate, that is indium selenide. Indium chalcogenates are attracting much interest due to their potential application in optoelectronic and thermoelectronic devices. Among them, indium selenide attracts considerable attention. INX-SCY exists in wide range of stoichiometric composition like INSC, IN2SC3, IN4SC3, IN5SC7, IN6SC7, and IN9SC11. INSC and IN2SC3 are extensively studied in photovoltaic devices, solid-state batteries, etc. So in the present study, I am going to focus on IN4SC3. So in the present study is focused on the preparation of IN4SC3 thin films by reactive evaporation techniques and the fabrication of a heterojunction diode using copper as the Schottky contact for high-speed switching and a low voltage rectification. Now, my preparation technique is vacuum evaporation. There are 4 stages in vacuum evaporation: transformation of a material from solid or liquid state to gaseous state, transfer of gaseous particle from source to substrate, deposition on the substrate surface, rearrangement over the substrate surface. Under vacuum evaporation, I focused on reactive evaporation. In reactive evaporation, the elemental sources are kept inside the vacuum chamber, and they are heated at a different time. And due to this elevated The need to synthesize the compound from elements prior to deposition is eliminated. The decomposition of the compound upon heating in vacuum can be avoided. The stoichiometry can be adjusted by varying evaporation rate, and the dopants can be evaporated simultaneously so that the uniform dispersal of the dopants are possible. Now, in the present study, the impeachment rate of indium and selenium are 2.7 into 10 raised to 15 and 2 into 10 raised to 15 respectively. Now, this is the X-ray diffraction pattern of IN4-SiO3 thin films, and using Scherer formula, the crystallized size is found to be 48 nanometer. A comparison of the sir, I am audible.
Sir, you are audible.
But your slide is not
Your,
visible.
your slide has stopped.
Yes. Okay. Is it clear, sir?
No, sir.
Okay. I will. Sir, is it visible now?
Yes, sir.
Okay. This is the XRD pattern of the IN4-SiO3 thin films. Now, using Scherer formula, the crystallized size is found to be 48 nanometer.
I think there is issue of network.
He's having some network issue.
Yeah.
Is it visible now, sir? FSM?
Yes, sir, we can see. Please go ahead.
Okay. This is the FSM image of IN4-SiO3 thin film. The average particle size is found to be 300 nanometer. The electrical studies of IN4-SiO3 thin films are carried out. The sample shows a resistivity of 23 ohm centimeter and mobility of 3.12 centimeter square per volt second. The carrier concentration is 8 into 10 raised to 16, and the carrier type is N-type. This is the XPS analysis on the prepared sample. The sample shows an atomic composition of 56.8 for indium and 43.2 for selenium. This is the talk plot of IN4-SiO3 thin film. The sample shows a band gap value of 1.65 electron volt. Finally, Schottky diodes are fabricated using copper as the Schottky contact on FTO coated glass plate. The IV characteristics under reverse bias and forward bias are shown here. On the left-hand side, we have the IV characteristic under reverse bias. It shows a voltage of 2.5 volt and a forward bias voltage of 0.7 volt. So this is our conclusion. Using reactive evaporation technique, nearly stoichiometric IN4-SiO3 are deposited on glass substrate. XRD and SEM confirms that the samples are polycrystalline. XPS analysis shows that the prepared sample is nearly stoichiometric. The sample shows a band gap value of 1.65. The film is N-type. Schottky diode is fabricated on FK coated glass substrate. The diode shows a forward voltage of 0.7 volt and a breakdown voltage of 2.5 volt. And our study shows the potential of this material for low voltage rectification and high speed switching application. I would like to thank Dr. B. Pradeep, Professor, Department of Physics, CUSAT, for guiding me throughout the research process. And I am thankful to ICC India organizers for giving me an opportunity to present. Thank you.
Okay, thank you, sir. I think in spite of all the network issue, you have presented well. Thank you so much, sir. So, Dr. Manoj Singh,
yes, sir,
only two presenters, the G0005, M. Sripat, and G1006, Chinta Madhubabu. They could not present. So, I have written 2-3 times the message on the group.
Okay, sir. So, I would like to thank Dr. Santosh Mani sir and Dr. Sumit Bhardwaj sir for chairing this session very well and handling all the presentation with proper questioning to every participant. So I think everyone enjoyed this session very lot. So I think no one is left for the presentation now.
Sir, I
We
can
are,
see
yeah,
one message I can see.
yeah, but we can include this in the next session.
It is
Okay.
Meenakshi Rana Vyas. Yes.
Yeah, we will include her in the next session.
Okay.
So thank you all of you for joining us, and we
Okay,
can
sir. Thank you.
conclude this
Thank you, sir.
session.
Thank you.
Yeah, we are going to conclude this session, and again joining the new meeting. Thank you, sir.
Thank you, sir. Namaste.
Okay, sir.